Welcome back to data mining. In this module, we'll talk about linear models.
Here's what you will learn in this module. We will first talk about what a linear model is and does, and then when linear models are appropriate for data analysis. Next, we will use simple linear regression and multiple linear regression to build a model of the data in a data set and then analyze the data in Python. Finally, we will evaluate models with important quality metrics.
So first, we're going to talk about linear modeling with regression. Regression allows you to estimate how a dependent variable changes as the independent variable or variables change. Input variables are called predictors. They are typically numeric and continuous, and the output variable, also called the response variable, is also typically numeric and continuous. When analyzing the data, regression comes up with a function or a model, which is what we're seeing here in this yellow box, based on the predictor variables that provides you with the best fit line or curve for the response variable. Now, it's important to understand that any response variable that the model calculates is, in fact, the result of the model and not of actual reality. So, regression models describe the relationship between variables by fitting a line to the observed data. Linear regression models, such as simple and multiple linear regression, use a straight line. That's what we can see here with the equations. For simple regression, we have one input variable with one coefficient m times x plus b. With multiple regression, we have multiple input variables. We have an x1, we have an x2, and we also have multiple coefficients, m1 and m2, and so on. Now, logistic and nonlinear regression models use a curved line, which is what we will see later. All in all, though, regression allows you to estimate how a dependent variable changes as the independent variable or variables change. So let's look at simple linear regression now. We use simple linear regression to describe the strength of the relationship between two variables. We can also use it in order to predict the value of the dependent variable at a certain value of the independent variable sometime in the future. This here is our basic equation, and in order to arrive at this equation, we have a number of assumptions. The first assumption is called homoscedasticity, which means that the error in our prediction does not change much across the independent variable. The second one applies typically to multiple regression, but it's really the independences of observations, meaning that there are no hidden relationships among the predictors themselves. Then thirdly, we want to ensure that the data follows a normal distribution, and fourthly, that it lends itself to a linear analysis. So let's assume that we work for a manufacturer of personal wellness products and that it is our job to forecast the sales of bottles of sunscreen based on the forecasted hours of sunshine for a week. Here, our X attribute contains the hours of sunshine from Monday through Friday. And in our Y attribute here, we have the historical sunscreen sales also on a Monday through Friday basis. We see that our N is 5 because we have 5 numbers here. How do we arrive at our equation in the format of Y equals mx plus b? Here's how. So for each x and y point, we have to first find our x squared and our x times y, which is what we're doing right here. Then we're going to sum all of these, which gives us our sum of our x, our sum of our y, our sum of our x squared, and the sum of our x times y attributes. From our previous page, we remember that we are looking for y equals mx plus b. We have these values calculated that we need in order to calculate our slope, our intercept, and then assemble our entire equation. And we also know that our n, that is the number of data points that we have, is 5. So first we're going to calculate our slope m. Our slope m equals the number of data points multiplied by the sum of our x and y attributes minus the sum of our x attributes and the sum of our y attributes. We divide that by our n multiplied by the sum of our input attributes squared minus the sum of our input attributes, and that as a square. So that gives us these numbers here, and we end up with an m value of 1.5183. The next thing we calculate is our intercept. In order to calculate our intercept, we need our m value here. This is why we're calculating the slope first. So our intercept b equals the sum of our y attribute, the sum of our dependent attribute that is, minus our slope m times the sum of our input attributes. And we divide all of that by the number of data points n. So that gives us 41, which is this here, minus 1.5183, that's our m here, times the 26, and that divided by 5. That gives us 0.3049 as our intercept b. Now we're going to assemble the equation for our line y equals mx plus b, which gives us y equals 1.5183 times x plus 0.305. Now that we know what our model looks like, namely y equals 1.518 times x plus 0.305, we can calculate the dependent variable values based on our model. And we're seeing here that the output that we're getting from our model is different from our actual reality. We call this difference the error, and this error will become important in a little bit. But what's important is that if the weather forecast now predicts 8 hours of sun, we can now use our model to predict the following sales. We can say 1.518 times 8 plus 0.305 gives us 12.45 bottles of sunscreen that we can sell. And if we want to see this on this graph here, all we have to do is just make a line here with our 8 hours, our input attribute, and it will intersect our model line, our best fit line right here at 12.45. So previously we've seen that the y values, that is the dependent variable values that our model calculates, are different from the y values, that is the dependent variable values that we know from reality, right? So how do we get to this fit line at all? Well, we get to this fit line by making the total of the square of these errors as small as possible, and that's how our fit line becomes optimized. So that when we square each of those errors and we add them all up, the total is as small as possible, and that's what we call the least squares. Now, these errors here are also called residuals. A residuals is a measure of how well a line fits an individual data point. Residuals should do the following. They should center around 0, they should follow a normal distribution, and they should not follow any pattern. How can we tell? Well, we could turn our diagram such that our fit line in fact becomes our 0 point line, our y line, and then we look at the distribution of the errors on each side. Does it center around 0? Do they center around 0? They sure do. Well, do they follow a normal distribution? Well, just about, right? Then do we see any detectable pattern? Not at this point, because we have 3 on one side, 2 on the other side, and none of these have the same value or the same distance from the 0 point. So this regression model looks to be of good quality. Now let's look at linear modeling in a different data set, fuel efficiency in cars. We remember in the fuel efficiency in cars data set that the attribute GPM, which is gallons per 100 miles, and MPG, miles per gallon, are essentially congruent, which means that we can drop one of these in order to make our processing easier and faster. This is exactly what we're doing right here. We're going to drop the MPG again so that our dependent attribute for the remainder of our analysis will remain gallons per 100 miles, or GPM. Then we are using this code in order to plot the independent variables against GPM. Here shown as an example is weight. Here's what a simple linear regression looks like with the stats models package. We first import the stats models package as SM, and then we declare our X and our Y, that is our predictor and our response, and we make sure that we add a constant as well. Then we build our model with the OLS, the ordinary least squares model for Y and X, and we're going to fit this model, which means we're going to build this model, and then we're going to pull out the summary. In the summary here, we can learn a whole lot of things. The first thing we're seeing is that our R-squared value is at about 70%. That means that 70% of the variation in GPM can be explained by using NC, that is number of cylinders, as the predictor. Secondly, we're seeing the coefficient table right here. The constant is 1.0581. And the coefficient for number of cylinders is 0.6, which makes our simple linear equation into GPM equals 0.6 times NC plus 1.0581. We're also seeing the other variables here, the standard error, our t-value, our p-value here with the confidence intervals. So this is the output of stats models, which gives you a very nice table. Here's what a regression, now a multiple linear regression, looks like in scikit-learn. First, we're going to have to import the linear model from scikit-learn. Then we declare our variables. For X, the input variables or the independent variables. Here I have selected all of the variables that I'm interested in from our data set. And our Y is the response variable, GPM in our case. After that, we build our linear model here, the multiple regression linear model. We use the linear model.linear regression function from scikit-learn and apply the model with lm.fit, lm being the alias that I've built here. Now, scikit-learn is a little bit different than stats models. It's not as pretty, which means that we have to retrieve any of the numbers that we are interested in. So here, for example, we can retrieve the R-squared score with lm.score. We're seeing that the R-squared score here is 91%. That is very nice. If we are interested in the coefficients for the predictors because we want to build the equation by hand, we can retrieve those with lm.cof underscore. And if we're interested in the intercept, certainly we can retrieve that with lm.intercept, also with an underscore. Awesome.
Here's what we've done so far. We have defined a linear model. We have determined when linear models are appropriate for data analysis, and then we've used simple linear regression and multiple linear regression to build a model of the data in the dataset. We have analyzed the data in Python, and then we have seen ways to evaluate models with important quality metrics. Thank you so much, and I look forward to seeing you in a future module.